Part B, we're asked to find a series expansion for f prime of x and its corresponding interval of convergence. All right, so f prime of x, we've taken the derivative of f of x, so we're taking the derivative of this power series. And we know from a theorem from advanced calculus that we can take the derivative of a power series term by term. In other words, instead of adding it up and then taking the derivative, we can take the derivative of each piece and then add them up. So if you go on and take some advanced math courses, you'll prove some theorems which will tell you exactly when you can do this sort of thing. You can't do it all the time, but in power series, things are well enough behaved you can get away with that. Okay, so let's see what this is going to be. As far as x is concerned, the negative 1 to the n and the 3 to the n plus 1 are constants. So they're just going to go along for the ride, constant multiple rule. And now I take the derivative of x plus 2 to the n power. And once again, n is a constant. So it's n times x plus 2 to the n minus 1 times the derivative of what's inside, that's just 1. So this is all over 3 to the n plus 1. Now, when you take a derivative, the constant term always drops off. And so if I look at where I'm going to start this power series, this series started at n equals 0, but at n equals 0, when I plug this in, I get a constant. This, by definition, is going to be 1. And so we get negative 1 to the 0 over 3 to the first, I get 1/3. That means that when I take the derivative, this term drops out. And we can see that down here. If I plug in n equals 0, I'm getting a 0 in this term and it's dropping out. That means I'm going to advance the counter to n equals 1. And so I've got n equals 1 to infinity. And that's a formula for f prime of x. Now, what's its interval of convergence? Well, I look at the interval of convergence for the original function, negative 5 to 1. And once again, we know that from a theorem in advanced calculus that the radius of convergence for this function is going to be the same here. So in other words, it's still centered at 2. I converge up to 3 units either side. The only thing that could happen when you take a derivative is you could lose endpoint convergence. Okay, so when I go from f to f prime, the only thing that could happen is I could lose endpoint convergence. But I didn't have any endpoint convergence to begin with. So I can say that without doing any of the mathematics at all, just using the theorems here, that the interval of convergence is the same as the original, negative 5, 1. All right, there are no endpoints to lose, so I don't have to check the endpoints. That'll do it for part B. All right, in part C, we're asked to find a series expansion for the antiderivative of f. And since we differentiate term by term, we anti-differentiate term by term as well. So I need to take the antiderivative of this function. So I'm going to anti-differentiate each term. Now once again, as far as x is concerned, all these n's are constant. So the negative 1 to the n and the 3 to the n plus 1, they just go along for the ride. And I anti-differentiate x plus 2 to the n. I get x plus 2 to the n plus 1 divided by n plus 1. Plus, of course, a constant. All right, so that's a formula for the antiderivative. Now I have to look at the interval of convergence. So the interval of convergence for the original function was negative 5 up to 1. And once again, the radius of convergence is going to be the same for the derivative and the antiderivative. So I know that my integral will converge at least on this amount. But As we talked about in class, as we go from f to the integral of f, there's a possibility we could gain endpoints convergence. So it's possible I pick up -5, it's possible I pick up 1, it's possible I pick up both, it's possible I pick up neither. The only way we're going to find out is we have to check the endpoints. So check to see if we gain endpoints. So do that on a case-by-case basis. So let's check x equals -5. So I've got to plug -5 into my formula for the antiderivative. Alright, so I'm plugging it into the antiderivative formula. Which I'll just recopy here. For reference, we've got that constant there. That's not going to affect the convergence of the series or not. So we'll just focus on the series part. So when I plug in x equals 5, I get -1 to the n, -5 plus 2 to the n plus 1 over n plus 1, 3 to the n plus 1, which is the series n equals 0 to infinity, -1 to the n, -3 to the n plus 1 over n plus 1, 3 to the n plus 1. And so once again, I've got the same exponent on these 3's, and so I can take advantage of that to simplify. That's -3 over 3 to the n plus 1, which is -1 to the n plus 1. So I get the series n equals 0 to infinity, -1 to the n, -1 to the n plus 1 over n plus 1. So how can I combine these? A couple different ways I can combine these. I can just add the exponents. I've got the same base, I can add the exponents. It gives me -1 to the 2n plus 1. Or I can rewrite this as -1 to the n times -1. So this is a 1 to the n times -1, which is -1. Here, 2n plus 1 is always odd, and so -1 to the odd power is -1. So no matter how you slice it, I get -1 over n plus 1. And now I have to figure out whether or not that series converges. Okay, so here's the series we get when we plug in -5. It looks a lot like a p-series. In fact, if you write it out, you'll see it is a p-series. And we've seen this before. If we shift the counter, so if we let k equal n plus 1, so that n equals k minus 1, then n equals 0 corresponds to k equals 0 plus 1, or k equals 1, up to infinity, -1 over k. And so this is going to diverge because it's a p-series, and p equals 1, which is less than or equal to 1. So this one will actually, because of the -1 there, that's going to add up to -infinity. Okay, so that means that -5 doesn't work. Now we have to go check the other endpoint. Alright, now we got to go check the other endpoint. So the other endpoint to check is x equals 1. So we're going to plug that in to the series, and we get the summation n equals 0 to infinity, -1 to the n, 1 plus 2 to the n plus 1 over n plus 1, 3 to the n plus 1. That's summation n equals 0 to infinity, -1 to the n, 3 to the n plus 1 over n plus 1, 3 to the n plus 1. And we can see those immediately cancel out. Get the sum n equals 0 to infinity, -1 to the n over n plus 1. Now, as we look at this series, it certainly appears to be an alternating series, and in fact it is. If you write this out, this is the world famous alternating harmonic series. This will converge by the alternating series test. So what does that mean then? We put all this together. The interval of convergence for the antiderivative is at least -5 to 1, but since we integrated, we could pick up endpoints. We found that the series still diverges at -5, but now it converges at 1. So that'll do it for part C, and that'll do it for checkpoint quiz 15.